Now I'd like to introduce our next speaker, who will be speaking about image annotation and data curation. Jayshree Kalpathi-Cramer from Boston, United States. Please.
Thank you so much for the opportunity to speak here, the invitation, and the support of the foundation. I have to say this is one of the most spectacular locations in terms of venues here, so I really appreciate this. So I'm going to be talking a little bit about annotation and data curation today. How many data scientists or computer scientists in this room? Okay. I suspect many of you would agree with this chart in terms of the amount of time that is spent on the various subtasks within creating a model in machine learning. Essentially, when surveyed, most people would say that most of the time that is actually goes to creating a model is spent on what some of us may think of as the more boring parts of the job, is finding the data, cleaning it up, curating it. And that really takes a substantial amount of time. And also the part that's least enjoyable. Hopefully this talk won't reflect that in terms of being the least enjoyable part of the process, but it really is something that is very necessary, but is also very, can be painful. And it was something that came up a lot earlier today with the questions from the audience is how does one actually go through this process of curating the data, creating a collection, and creating a model. So just very briefly, as you've heard a lot before, a machine learning system is something that gets better through experience. So many of the components of creating machine learning systems are having lots and lots of data with lots and lots of outcomes that you want to essentially build the system to start to predict. And we have data that goes in. We have a model that transforms the input into the output. We have some model parameters that essentially say what the model does. We often try to minimize a cost function that is the difference between the correct answer that we want and something that the model predicts. And then the algorithm is something that optimizes these parameters. So one of the questions is, what are the different kinds of these machine learning algorithms that one might think about? And there's many different ways to characterize that. So it depends on what one way to think about it is supervised or unsupervised machine learning. In supervised machine learning, for instance, you have data with known truth. Benign or malignant is a classic example of that. And you're trying to find a classifier that can then do the same task. In unsupervised machine learning, you don't necessarily have the ground truth. But what we're trying to do is find clusters similar objects or patients or characteristics together. So here you're just essentially putting the data and seeing what things start to group together naturally. Another way of thinking about it is in the kind of model that you're going to be building. So this might be a neural network. You've heard a lot about support vector machines or LDAs or other classifiers. You might have decision trees. So all of these are different ways of creating machine learning classifiers. Not finally, but next we might want to think about what the task is. Is it a classification task? So again, this would be something like, is it benign versus malignant? Is it a regression task? Are you trying to predict something that lies on a continuous scale, for instance? Are you trying to generate data? Are you trying to reconstruct data? So it really depends on the task at hand. And the reason we have to think about all of this is as we are creating and annotating the data, the annotations depend very significantly on the task that we're trying to accomplish here. Then we might want to think about the application. So is it a reconstruction, for instance? So machine learning and deep learning specifically are being used a lot in the reconstruction domain. So going from raw data, whether it's K-space data or sinograms, to the reconstructed image. It's, again, a really great and exciting application of deep learning. The kinds of data you need to curate for that task is very different than a task where you might want to say, is it a benign or a malignant lesion? So you might want to have a object localized or detected. So given a scan, where is a nodule of concern, and that might involve having a bounding box or some kind of a heat map identifying the area of concern. You might want the segmentation that people talked about. So for a lot of things, including for radiomics, you might want a nice, precise segmentation of the boundaries of the tumor. You might just want to know if it is benign or malignant. So it really depends on the task that you're trying to accomplish in terms of the kinds of annotations that, and the curation that we might want to do here. So again, reiterating that. The annotations can occur at many levels. So what is it that we are trying to annotate at what level? So is it, depending on the task, you may want to annotate at the patient level, at the slice level, at the image level, at the voxel level. You might want to annotate, depending on where you're getting your data from, so we'll discuss this in a little more. How are we going to do the annotations? How many cases does one need? So these are the typical questions that need to be addressed when deciding the process of curating and annotating your data. So depending on the task, we may want to annotate it at the patient level. So for instance, on a scan, you might know that this patient has a malignant or a benign lesion, cancer or non-cancer, so we might have information only at the patient level. We may have information at the image level. So for instance, maybe the disease is seen on a particular kind of scan, and you know that, again, at the global level of the scan, somewhere in this 3D volume is the presence or absence of some finding, or maybe on this mammogram, we know what the breast density class is, for instance. We sometimes might want to annotate at the slice level. So again, if you're looking at a CT scan, you may say, these are the slices where there's a lesion, for instance, or you might actually want to know the presence or absence of that finding on a voxel level. So depending on what the task is, the annotations have to reflect that and have to be done at these various levels. We heard a lot from Chuck Khan and others about how best to do the annotations. So very typically what we tend to do now is do it retrospectively. So we go into our packs and go into the radiology report, try to retrospectively look at the data, to pull data from the packs and the reports and try to figure out which of the cases that ended up have some finding of interest. This can be dangerous, as was mentioned, because, for instance, if you're talking about the pneumothorax or something and you look for the report that has that word, you may not know that the system will end up finding is tubes or something else. So we often, if you look for osteoarthritis, for instance, you end up finding all of these x-rays of post-surgical with knee replacement, and they're not really good for the task we're trying to do, which is creating a classifier for the task. So there are some concerns about using purely retrospective data that was not created for the purpose of this task, but it is essentially what we tend to do because that's what we have access to. Ideally, we'd like to do what Dr. Khan proposed, and that have a way of annotating data in a nice way going forward so that the annotations are useful both for the workflow as well as for creating the machine learning algorithms later. The next thing that we tend to do is have experts annotate them. So very often we start off with pulling data from the packs. We have a rough idea as to whether they're benign or malignant or whatever the other finding is. And then we have somebody go through and say, yes, no, yes, no. If you wanted segmentations, for instance, we may have experts manually outline all of the tumors. That's the next step in that process. Some of this, of course, when you relying on the experts to provide the annotations, it is in some ways an opinion, not necessarily the ground truth. So potentially we might want to go into the pathology report, for instance, and see if there was a biopsy that was done. That may be a better ground truth than just a expert opinion as to the ground truth. And then ideally, we might actually want to look at outcomes. So for instance, if you're looking at pseudoprogression versus true progression, we may not really know the answer to that till we wait and watch and see what happens to figure out the true outcome. Or if you're trying to predict survival, we may actually have to wait to have that survival information. So the quality of the annotation and the quality of the ground truth really can vary as you go through this process of just pulling data from packs and looking at the radiology report to actually waiting till you have some kind of a ground truth around it. So so I'm going to next walk through a set of case studies in terms of some examples that we've done in our lab and the kinds of curation and annotation process that we went through to develop these models. So the goal, this is some work that we did recently with the ACR Data Science Institute, and the goal here was to develop a automated tool for breast density classification. So the specific task was to essentially classify a mammogram into one of these 4 classes, almost fatty, scattered, heterogeneous, and extremely dense. And this annotation we were doing at a patient level. So the data that we were using was a data from a clinical trial where each site had a radiologist annotate each case, and this was done at a patient level. So looking at both left and right breast, as well as all of the available views at a patient level, there was a decision made as to put that into one of those 4 classes. And from that, we then, so this is the second of the annotation plan is what we used for this particular study. At a previous study that had been showed earlier, for instance, that was a single institution data set where the data came from the PACS. In the third version of this, what we're planning to do now at the ACR next week is actually have a crowdsourcing event where we're going to make available a bunch of these cases and have all of the participants annotate them, and then we're going to build a model from that and see how that compares to the models that were built from the single ground truth that we got from during the clinical trial or the single institution data set versus the crowd. So here again, going back to the same data from the DMES trial, for instance, this was data from multiple manufacturers. So it was a multi-institution study where each site was doing the annotations separately. It was at the patient level. We created using a very fairly standard CNN. We used a resonant architecture, and we got pretty good performance comparable to what was published, for instance, more recently. You have both 4 and 2 class, and you can see where the misclassifications tend to be. The next question that typically tends to be asked is, how many cases do I need to do this? And usually the answer for all of these is it depends. So it really depends on the task. So in this particular case, for the task of creating breast density models, you can see that the performance starts to level off by the time you have up to like 6,000 to 8,000, maybe 10,000 images, you're at a fairly stable level. On the other hand, if you don't use something that was mentioned previously of the idea of using pre-trained networks, so these were networks that were generated for natural scene images of cats and dogs using ImageNet. If you use these pre-trained networks, you can get away with a lot fewer cases. If you're starting from training a network from scratch, you need a lot more cases. So you can see that at the lower curve is basically starting from scratch, and we are, even at 15,000 images, we're not at the performance that we need to be achieving. Another thing that keeps coming up is the fact that these models can be not very robust. So if you build a model at one institution and then try to apply it at another institution, both for deep learning and radiomics, we see a lot of challenges with that. Here's an example, again, from this study where we have 3 different manufacturers of tools and models that were built specifically for those 3 manufacturers versus a model that was built for essentially combining all of them together. And what we see is that if you take a model built on essentially manufacturer A and it works okay, but then if you apply it to manufacturer C, it basically falls apart. So this is something that as one is evaluating these models, one has to be really aware of, is that the performance that the vendor might quote may not necessarily reflect the performance at your site, because it may have been built with data using, for instance, different parameters, different different acquisition tools, different protocols. So it is really important as you're evaluating these tools is to have a really well curated data set against which you can check the performance of these different tools. So even if you're not building your own tools, I think the process of curating a data set to evaluate these tools is really important. The other thing to say is that to the extent that you can build these models using data from multi-institution data sets, the better these models tend to be. And again, things like distributed and federated learning can help in that. The idea with these distributed and federating learning systems is that you can build a model across institutions without the data leaving the institutions. So the model parameters are shared between institutions. You can sort of collaboratively build a model but there's so many concerns about the data leaving the institution that sometimes that's not practical, and some of these distributed and federated learning systems can help you mitigate those risks. So here is an example of an annotation tool that the ACR has been building, especially for this, both for the Data Science Institute as well as for the crowdsourcing contest coming up shortly. And again, it's a fairly straightforward web-based image viewer. The goal is to essentially classify at a patient level the breast density. The goal with building this as a crowdsourcing thing is to hopefully make it a seamless process that you can just sort of click and have the next case come up. And so we're hoping to get lots and lots of cases annotated this weekend and next week. Does it really work? It's a good question. It depends, again. One of the reasons we like doing crowdsourcing is that we've seen in general that annotators can be biased sometimes, and sometimes having consensus is a less biased version of truth to the extent that we can ascertain truth from asking people. So when we're doing crowdsourcing, one of the concerns is if we're going to get garbage, and it's usually fairly straight. If you have enough cases, annotations per case, you can fairly straightforwardly filter out garbage. So obvious mistakes, things like that can be filtered out fairly easily. The other thing one can do is actually have known cases with known truth interspersed within the unknown cases so that you can evaluate the performance of the crowd and just throw out those people who are perhaps not performing as well. So we've been running a crowdsourcing experiment at RSNA for the past few years and essentially asking people to come annotate cases from the Cancer Imaging Archive. It's been going pretty successfully. We're going to do it again this year. So if any of you are going to be at RSNA, please stop by and help us annotate some cases. Most people that came to the booth annotated somewhere between 10 and 20 cases. Some annotated hundreds of cases. And we certainly met our goal of having all cases annotated by 3 to 5 people at a minimum. And when we compared what the annotations were compared to ground truth, we got pretty good agreement. And in fact, we found that when we had multiple experts creating the ground truth versus the crowd, the variability among the crowd was not that different from the variability among the experts. So in some ways, it's a reasonable approach to get a lot of data if you want it annotated. So here's an example of some of the more extreme differences, and you can see again it is not that bad in terms of what was annotated. The numbers are different, but it was approximately the same size. It was just how precise people were being in terms of finding the exact boundary. In terms of the next thing that I was going to talk about is looking at response assessment in brain tumors. So the goal here, I think that again came up a lot this morning, is something that radiologists seem to want, is a tool to do volumetrics, whether it's tumors or mets. So automatic segmentation to the extent that we can is a good tool. Brain is certainly easier than many other organs, so that's probably why we started there. But it's specifically we are trying to annotate, get segmentation on brain tumors given T1 pre and post contrast, T2 and FLAIR images. And we had the 1 to 2, actually more than 2 people annotate each case with whole tumor enhancing tumor necrosis and so on. And then the segmentation was the output of the network. In this particular case, because we are actually doing segmentation, and although each voxel is not exactly independent, we can get away with a lot fewer cases. So for segmentation, we've typically found hundreds of cases is probably a reasonable start to get good segmentation, unlike the hundreds of thousands of cases you may need for other tasks. And so we have a toolbox here that allows you to segment brain tumors. So that it's all open source, so there's a tool out there. You can just go get it and try it out and let us know if it doesn't work for your data. So this essentially is a deep learning tool that segments it. It's always fun to watch what the network is learning. So one of the questions that keeps coming up is, what do these black boxes do? And if you actually save out the output during the training process, you get a pretty good idea of what the network is actually doing during the learning. And you can see when it starts off, it thinks the whole brain is a tumor. Then it has maybe the sagittal sinus or other things that are enhancing as a tumor. And then as it goes along the training process, it gets much smarter about being able to separate the tumor from other enhancing areas. very standard network. The other thing that we can now do is actually automatically do RANO measurements, so not only have the volume, but also have bidirectional measurements, and what we now can compare that with what humans experts have for the response assessment and so on, and see how well that response. So this a very similar thing is brain METs compared to GBM. Again, in some ways it's a very similar task, but obviously the difference is you have lots of small objects as opposed to one big object. So even though in some ways the annotation is similar, the optimal network may not look exactly the same, because if you look at something like dice score, which is typically used as a way of training the networks, it doesn't penalize missing out a lot of these small METs. So you tend to have a network that does a really good job of finding the big METs, but doesn't do as good a job of finding the small METs. So making sure that the human annotation annotates each of those small METs is important if you're training a network for METs compared to something like the brain tumors. The other thing that was mentioned was the ability to now do longitudinal tracking. So here's an example of where we can then essentially see which tumors, again, the task of annotating each MET and trying to see which one is growing and which one is stable and which one is shrinking can be very painful, and deep learning type tools might be able to help with that. So here's a visualization of the color coding says which ones are growing, which ones are shrinking, and the average size is essentially the size of the tumor. So this was, now if you're going back to a different kind of data set where you're trying a different task, it's not necessarily screening, but if you're talking about lung cancer, for instance, and we had the Kaggle challenge where the goal was to say, given a CT, can you predict which of these patients will be diagnosed with cancer within 1 year? In this particular case, the data set was annotated by just a spreadsheet. Here's a CT, here's a 1-0 as to whether that patient was diagnosed with cancer within 1 year or not. So that is a very different type of annotation than, say, the one you might want to say predict malignancy versus not, where you're using radiomics, where you might now want to have the lesions segmented out. So if given a lung nodule, you're trying to predict whether it's malignant or not, has a completely different, potentially, way of annotating the data set. Here you might have, for each of those, you might have a boundary, you might say which ones are malignant or not, and that may have been biopsy proven. If you have now, the other scenario is follow-up. Given a pair of scans taken 1 or 5 years apart, which of them actually were cancer or not? Again, the data set curation process is different, because now you have two pairs of images, and a ground truth that may just be a 1 or a 0 as to whether it's cancer or not. Looking at the IDH and virtual biopsies were mentioned a lot. Here, the goal is to predict based on just imaging as to whether this patient is the brain tumor is IDH mutant or wild type. A typical approach that has been done a lot is radiomics. This is some recent work where we had 600 plus patients, and this was the steps that we do typically. The first step typically tends to be approximately segment the tumor, extract features, do the classification, and so on. And so based on that, we get a pretty good performance. The same thing you can do with deep learning, just directly feed the image and again predict the output. One of the considerations for all of this is humans can be quite variable. What we see is, this is not for cancer, but this is a different task. We gave the same image to 8 different people, and they were putting it in a 3-class disease severity problem classification. And we find that one person will say it's class 1, normal, one will say it's pretty bad. And so we see so much variability in the sensitivity and specificity of the humans that are doing the annotation. Going back to the question of whether you want to customize it or standardize it, it's a really good question, because if you standardize it, you'll be somewhere in the middle. If you customize it, you'll be at extreme ends of that. And we get very different answers when we ask clinicians what they prefer. The department chairs and the quality people always tell us, make everything the same. But when you talk to the individual clinicians, they're like, no, make it look like me. I want to fine-tune it to where I am. So that's something I'm looking for a comment from everybody here, is whether we want to be able to dial our systems to where we want to be. And there's a number of pitfalls in terms of data curation, in terms of data leakage and confounding and so on. So we have to be very careful about making sure when we're curating these data sets that there's no leakage between the training and test data sets. This happens a lot in published literature, surprisingly. It's pretty scary, actually, how often this happens, that there's not very clear separation between the test set and the training set. You'll see things like even slices, people mixing up the slices between the training and the test, or doing some fairly horrible things. So be very careful about that part of it. Sometimes the confounding factors, like you might create the cancer cases from a certain time and the normals from a different time, and the scanner manufacturer changed in between, and what you ended up picking up was a manufacturer as opposed to anything about the disease. So being very careful about how you curate those data sets, about the population, about the location, all of that is really, really important. So the sneak preview of the ACR work coming up this weekend. So there's a lot of interest from the previous questions about how do we get started, how do we get educated. The Data Science Institute is going to make available a bunch of resources around that, around the process of creating, of curating, of running, of evaluating, with videos and a whole bunch of things. So this is not ready yet, should be out this on Sunday, I think. So once it's out, I'd encourage everybody to go check it out and let us know what you think about that. So yeah, again, this is from Dr. Keith Dreyer's slide, but this lab is going to have all of these things. So learn, define, evaluate, create, and collaborate. So, and with that, I'd like to thank you all. And we are also looking for people, so please, please reach out to us. Thank you.